Alright, in this video we're actually getting to our first examples with integration. Integration, as you saw in the notes, can be thought of as the opposite operation to differentiation. So in our calculus class and in most standard calc classes, there are two kind of main computational skills that you learn: differentiation and integration. And the reason why you learn both of them is they're opposites, just like addition and subtraction or multiplication and division. So the integral, and we're gonna see that there are kind of two types that you need to know: indefinite and definite integrals. But in this video and this week, we're just gonna get started with indefinite integrals. The process for evaluating indefinite integrals is sometimes just called anti-differentiation. Usually these terms are interchangeable. So this is section 6.2. Hopefully in the notes you saw the formulas that you'll be using in order to integrate. Just like you had differentiation rules, you have the rules now, some properties that try to undo derivatives basically. So the first example is to evaluate the integral of 4x minus 3. This dx term just always tells you what variable you're integrating with respect to. So in our class, it's a single variable calculus class, so there should only ever be one variable. But the way that we read this is the integral of 4x minus 3x dx, or the indefinite integral of 4x minus 3x. This function 4x minus 3 is what we call the integrand. It's whatever is under the integral symbol, and that's what this squiggly line is. It looks like an elongated S or L, but it's an integral symbol. Okay. The main things that we're looking at in this example, you have 4x minus 3. One property you can use, I'll go really slowly step by step, but I have a feeling that in the next week or so you'll be able to do these much faster and write fewer steps. But let me start really slow and go one step at a time. So the integral 4x minus 3 dx, one of the properties we have is that whenever you have addition or subtraction, you can break it up into two integrals. And another property that we have is whenever you're multiplying by a constant, like this 4, you can take it out of the integral. So only the first one is being multiplied by 4. And I'll leave the 3 here. So it's just 4 times the integral of x minus the integral of 3. Okay, to integrate x, it's really x to the first power. Again, integration is the opposite of differentiation. When you differentiate something like this, the power goes down by 1. Since we're integrating, we should bump the power up by 1. But notice the derivative of x squared is 2x, not x. So to correct for this, we divide by the new power. And this is like how, in general, you anti-differentiate x to any number. One of the main properties that you'll use over and over again is that the integral of x to the n dx is 1 over n plus 1, x to the n plus 1. This should make, plus some constant. This should make sense because when you differentiate 1 over n plus 1 times x to the n plus 1, the process that you follow, the power rule, tells you to bring the n plus 1 down, but n plus 1 divided by n plus 1 is just 1. So that's why you have this coefficient 1 here, and your power decreases by 1, leaving you n. So you can see that we're just going backwards now. Okay, another integral property that you have is that when you integrate a constant, it's always just that number times x. And we always tack on some unknown constant at the end because, as is mentioned in the notes, your integrals for indefinite integrals, they're not unique. You can see this easily by considering, let's say, x squared plus 1, x squared plus 10. These both have the same derivative, 2x. So when I integrate 2x, I don't know what the constant is. So we signify that by writing a capital C here. So let me go ahead and simplify this. 4 times 1/2 is 2, x squared minus 3x plus c. And this is the final answer. So even though this is a new computational skill and it's a little bit hard because you're going backwards from this thing that you just learned, differentiation, you can check your answer very easily. If you integrate this and if you differentiate 2x squared minus 3x plus c and get 4x minus 3 back, then you've done the problem correctly. So if we take our answer and differentiate it, 2 times 2 is 4x, derivative of negative 3x is negative 3, derivative of c is 0. Notice I get the integrand back. So I have done this problem correctly. Okay, in example 2, I'll go a little bit faster. I'm not going to break it up into separate integrals. The antiderivative of e to the x is just itself. This makes sense because when you differentiate e to the x, you get e to the x, so going backwards, nothing changes. For the next term, the 6x squared, I know I need to bump the power up by 1, and then I need to take whatever my old coefficient was and divide by the new power. 6 divided by 3 is 2. Same thing here. This is x to the first power, so I can bump it up to x squared. 10 divided by 2 is 5, plus some constant. Let's check by differentiating. The derivative of e to the x is e to the x, so that's good. The derivative of 2x cubed is 6x squared, and the derivative of 5x squared is 10x. And the derivative of c is 0. So this is the correct answer. Okay, and one last example for this section. We'll do more in lecture on Monday, but for one last example for the videos, let's look at this problem. Suppose you know that the derivative of a function is 3 over x plus 4x, and you know that the derivative at 1 is 2, and you want to figure out what the function is. So you have the derivative, you're trying to go backwards and find the function. That's exactly what it means to integrate, right? So what happens if I just try to integrate this function f prime of x dx? Well, let me write the expression explicitly. This one maybe looks a little bit tricky at first. Notice you can write this as 3 times 1 over x plus 4x dx. And writing it like this allows you to identify 1 over x as the derivative of ln of x. So when you go to integrate, integrating 3 times this will be 3 times ln of x, because the derivative of ln of x is just 1 over x. And integrating 4x, bump up the power by 1, take the old coefficient 4, divide by the new power 2, 2x squared, plus some unknown constant. Okay, notice in this problem, we are, oh sorry, this shouldn't say f prime of 1, this should just say f of 1, my bad. So it should look like f of 1 is 2. Okay, notice in this problem, we've only really exploited this piece of information, and we don't know exactly what the function f of x is. We know what it looks like, but we don't know what the constant c is. But we haven't used the fact that f of 1 equals 2. If we do that, this function, after you plug in 1 for x, should spit out 2, because that's what it means for f of 1 to equal 2. What happens if you simplify this? ln of 1 is 0, so you have 0 plus 2 plus c equals 2, which means c is 0. So actually, we know exactly that the function is 3 ln of x plus 2x squared. C happens to be 0 because of the information that we're given here.